Welcome to this video. Let's talk about stoichiometry of solutions. To talk about stoichiometry of solutions, we'll be looking at ways of expressing concentration. And there are three common ones that concern us. We call them molarity, molality, and normality. Now the first two sound alike, so take note of the difference, the L here and the R there. So molarity, we represent it in symbol as the capital M, and we pronounce that M as molar. So if I write 2 capital M, you pronounce it as 2 molar. Molality, the small m, we pronounce that as molal, molal. Unlike this, that is molar. So molar, molal. So if I write 4 and small m as a concentration, you pronounce it as 4 molar. Then normality is represented with the capital N, and that N is called normal. So if I write 3.5 capital N as a concentration, then you pronounce this as 3.5 normal. Now what do they mean, these three ways of expressing concentration? Of course, we know that every solution will made up of what? Solute and solvent. So here I'm showing solute plus solvent to give solution. In the case of molarity, molarity is concerned about how much solute is present in 1 liter, 1 dm cube, not of solvent but of solution. That's molarity. So we define the molarity of a solution as the number of moles of solute present in 1 dm cube of that solution. But when we're talking about molality, it is the number of moles of solute in 1 kilogram, not 1 liter, and this time not of solution but 1 kilogram of solvent. That's molality. Then finally, normality is number of equivalents of solute present in 1 dm cube of solution. So if you check, it appears like molality and normality have something to do with molarity. They share something, they have something in common with molarity. In terms of molarity and molality now, they are both moles, just that while one is per dm cube of solution, the other one is per kilogram of solvent. Then for molarity and normality, they are both per dm cube of solution. But while one of them deals with moles of solute, the other one deals with equivalents of solute. Having said so, the next thing I would like to show you is mathematical expressions for molarity, molality, and normality. These are 3 expressions. That one there is a formula for molarity. For most solutions you will encounter in exams, the molarity would easily be calculated as 1000 times the mass of the solute. So down here it shows that small m is mass of solute divided by volume of solution in cm cube. It is because this volume of solution is in cm cube that I have the 1000 there to convert it to dm cube. That means if I'm given a molarity question and this volume is in dm cube, then I would not need the 1000 anymore. But for now, the 1000 is there because this volume is assumed to be in cm cube. Then the mass here, this capital M, is actually the molar mass, like we said here, molar mass of the solute, okay? Since I didn't write double M's there, let me just put this as capital M. Alright, so the molar mass of the solute. Now think of it, mass of solute over molar mass of solute. That will give us number of moles of solute. It means therefore that molarity may also be written as 1000 times number of moles over volume in cm cube. But what if the volume were in dm cube? Then molarity would simply have been number of moles per dm cube, which is the definition we had at first. Then for molality, molality is 1000 times mass of solute divided by weight of solvent. If you check here, the W is weight or mass of solvent, but in grams. And that means the 1000 there is meant to convert that from grams to kilogram to match the definition. So if we are given the mass of the solvent in kilograms already, we would not need this 1000. But in many instances, it comes in grams, so we'll need the 1000. And then finally, for normality, we say normality is given as 1000 times the mass of solute times the number of reacting units. We'll give meaning to that when we come to normality. Then under here we have V, which is volume of solution, not solvent. And then the M there is molar mass of solute. So these three formulas are very useful when we calculate or we solve questions on molarity, molality, and normality. You may pause the video to look at this formula or make some jottings, because after now, I'll be looking at questions on each of them. Questions on molarity, on molality, and on normality. I'll solve 2 there. I'll solve 1 here. Okay, 2 for this as well. And then 1 for normality. After solving those 5 questions, I'll let this topic go. I'll let this video go so that by the next video, we could look at cases involving theoretical yield and actual yield, percentage yield, and all of that. So for now, let's make way. Let's try to see a question on molarity. We actually said we'll solve 2 questions on molarity. So let's see what kind of questions we could have on molarity. This first one says, calculate the molarity of a solution or a 300 cm cube solution containing 6 grams of calcium carbonate in water. Then we are given CaCO3 equals 100. See this question. Calculate the molarity of a 300 cm cube solution containing 6 grams of calcium carbonate in water. Now, typically, calcium carbonate is insoluble in water, but however that happened, we've been told now that 6 grams of it was dissolved in water to give a solution whose volume was 300 cm cube. Now, as a simple question that we have it, the molarity will be calculated just as shown as 1000 times mass over volume times molar mass. So that the molarity becomes 1000 times the mass of solute here is 6, divide, the volume of the solution is 300, times the molar mass of the solute is given to us as 100. If you check this well, you discover that it becomes 60 over 300, because this is 1, 10, 10 by 6 is 60. 60 over 300 is 1 over 5, and that gives me 0.2. Now the unit, capital M, which is pronounced molar. If you don't want to write capital M, you could also write that answer as 0.2 moles per dm cube. Still correct. So 0.2 mole per dm cube is the solution to this question. It is the answer to this question. So for this question, the molarity is 0.2 moles per dm cube. However, it is possible that we are required to calculate the molarity of a stock solution. What do you mean by a stock solution? Stock solutions are highly concentrated solutions, especially of acids, that we find in the lab. You may have observed in a lab before, you see some big brown bottles containing concentrated acid solutions. Those are stock solutions from which you can make dilute solutions for everyday practical work. So such stock solutions, how do we calculate their own molarity? We need that information, especially when we are going to prepare a dilute solution. All right? So when we calculate the molarity of stock solutions, we do something like this. Let me put a sample question here. It says, what is the molarity of a stock solution of H2SO4 of density 1.84 grams per cm cube and containing 98% H2SO4. Look at this. What is the molarity of a stock solution of H2SO4 of that density and containing 98% by weight H2SO4? If we're given this question in an exam, there's the conventional way of solving it, like you solve for some time and yes, you get the answer. But one simple method I have come to devise for solving questions like this, remember, this is a question on stock solution. It is different from ordinary molarity of dilute solutions like this. For stock solutions, the formula we commonly use, so this is molarity of a stock solution. The formula we use usually is 10 times P times D over M. So what are these parameters? P here stands for percentage composition. It's usually given to us. D stands for the density of the stock solution. They give it to us as well. And then M here stands for the molar mass of the substance in that stock. In this case, H2SO4. So I'm going to say now that the molarity of the stock will be equal to 10 times the percentage composition is given to me as 98 times the density there is 1.84, and then interestingly the molecular mass of H2SO4 is 98. If you calculate H2 plus S plus O4 you get 98, so I'll put 98 down here, and that means the molarity in this case will be 18.4 molar. That is our stock solution. So usually when we have stock solutions like that, we could carry out or we could calculate their molarity just as I have done using that simple formula that the molarity of a stock solution is 10 times percentage composition times density over molar mass. Now this stock solution of mine, if I were to make a dilute solution from it, there's this formula, the dilution formula, that I commonly apply. See what I mean? Here is my stock in a container, and I intend to make, let's say, 400 cm cube of 0.5 molar solution from this stock. What volume of this stock would I need and how would I carry out the procedure? Remember what I want to prepare: 400 cm cube of 0.5 molar for my laboratory work. But what do I have on hand at the moment? A stock solution. So how do I go about preparing this new solution? For ease, let's assume that this is my stock. I've calculated its molarity already and I obtained 20 molar as the molarity of the stock. What volume of that stock would I need therefore? I'll use the dilution formula, which says initial concentration times initial volume equals final concentration times final volume. Now the final volume and final concentration are the ones I want to achieve. They are right here. Then the initial concentration is the molarity of the stock, while the initial volume is the volume of stock I would need. So I'll have to calculate this as 20 molarity of stock times the volume of stock I would need equals the final concentration I hope to achieve times the final volume. So my V1 here will be 0.5 times 400 over 20. That gives me 10 cm cube. So it means that the volume of this stock that I would need will be 10 cm cube. Now this 10 cm cube of stock, what would I do with it? How do I use it to prepare that solution? Typically, because I know I am headed for 400, I could take a measuring cylinder that way, and then put water in it up to, let's say, the 300 cm cube mark, distilled water. Then to this 300 cm cube, I am going to pour in 10 cm cube of stock, and that means the total volume here will rise to around 310. Okay, then I'll add more distilled water to make the volume up to 400. At that point, I'll be very sure that what I have with me is 400 cm cube of 0.5 molar solution of this substance. So that's how we prepare solutions for laboratory use actually. We get the molarity of the stock, then calculate the volume of the stock that we would need. But sometimes they may give you this question without mentioning the word stock. They just give it to you like a normal question. For example, you could see something like, see this question. I want to put a question here. It's still on this, but let's see how we'd solve it. The same formula actually. It says, what volume of water should be added to 200 cm cube of 0.1 molar, or let's say 1 molar HCl to dilute it to 0.1 molar? That's the question. What volume of water should be added to 200 cm cube of 1 molar HCl in order to dilute it to 0.1 molar? Which means currently what we have is 200 cm cube of 1 molar, and our intention is to dilute it so that the concentration becomes 0.1. It means therefore that the initial concentration is the 1, while the initial volume VI is 200. So the new concentration we wish to achieve is 0.1 molar. So what will be the new volume, the final volume? Of course, VF from our initial formula there becomes CI VI over CF, which is 1 times 200 over 0.1, and that gives us 2000 cm cube. That means the volume we are going to, in order for the concentration to become 0.1, is 2000 cm cube. But they didn't ask us for that final volume. See the question. It says what volume of water should be added to 200. So 200 is there already. We need to add water to it to make it up to 2000. So it means that the volume of water to be added will actually be 2000 less 200. All right, so that gives us 1800 cm cube as the final answer. So that's molarity for us. We've talked about molarity of stock solutions, we've talked about molarity of dilute solutions, and then we've talked about the molarity of, or we've talked about cases where we dilute solutions. Using the dilution law, we can calculate the volume of stock that we need and so on. So at this point, I'll leave molarity to look at molality and normality. For molality, I already said that I will solve 2 questions. Those 2 questions will be on the board by the time we return from the break. Welcome back. Now the first question says, what is the molarity of a solution containing 10 grams of KHCO3 potassium bicarbonate in 50 grams of water? If we were to solve that question very quickly, we say molality, please, this is molality as well. Molality equals 1000 times, we said mass, over weight of solvent times molar mass of solute. So that the molality becomes 1000 times, the mass of solute there is 10, the mass of solvent KHCO3 is 50, and then the molar mass of the solute KHCO3, if you calculate it from those values given, you'll get 100. So from here, I have 1, I have 10, 10 by 10 is 100, divide that, it gives me 2.0 molar, or I write it as 2.0 with the small m. So it's simple. You just have 1000 times mass over mass of solvent in grams times the molar mass of the solute. So having solved that one, look at this second one, which is more difficult actually. It says calculate the molality of a solution prepared by bubbling 16 grams of SO2 into 205 cm cube of water. Now 205 cm cube of water is 205 grams of water, because the density of water, like we have always said, is 1 gram per cm cube. So on the basis of that, see what we have. When SO2 is bubbled into H2O, a reaction actually occurs. They will form H2SO3. This reaction takes place. So it means SO2 does not just dissolve in water to become aqueous SO2, but it actually reacts with the water to form H2SO3. And by this, by the stoichiometry here, 1 mole of SO2 will combine with 1 mole of water to produce 1 mole of H2SO3. This 1 mole of SO2 is 64 grams. If you calculate S and O2 from the provided values there, you have 64 grams. Then 1 mole of water is 18 grams. And then 1 mole of H2SO3, you can just add up here based on the law of conservation of mass instead of solving. But fine, if you want to calculate the molar mass from there, you could. But what you get here is 82 grams. So 82 grams of H2SO3 is obtained when 64 grams of this guy is dissolved in 18 grams of that guy. But now we're using 16 grams only of SO2. So what mass of H2O would that need, and what mass of H2SO3 would that produce? If you were to calculate the mass here, it would be 16 times 18 divide 64. That would give us 4.5 grams. And it means therefore that the 4.5 grams will combine with 16 grams of this to give us what here? 20.5 grams of H2SO3. So we have 20.5 grams of H2SO3 coming from 16 grams of this and 4.5 grams of that. So understand something, please. Assuming this were the reaction vessel at the start, what we had inside was water, 205, and then SO2, 16. But after reaction with the water, all of the SO2 was used up. H2SO3 was produced. What mass of H2SO3 was produced? We said 20.5 grams. Then the water, we had 205, but out of it 4.5 had been used. So if you subtract this 4.5 from 205, you have 200.5. All right, so 200.5 is the mass of water that is left here after reaction. That means by the end of this bubbling, what we actually had in the container was 20.5 grams of H2SO3 inside 200.5 grams of water. Does that obey the law of conservation of mass? Yes, it does. It does in that here in the beginning, 205 plus 16 will give us 221. And there at the finish, 200.5 plus 20.5 still gives us 221. So the law of conservation of matter or of mass is obeyed. Now from there, let's calculate the molality of this solution. So the molality now, molality will be equal to 1000 times mass of solute over mass of solvent times molar mass of solute. So the molality becomes 1000 times the mass of solute is 20.5 divide mass of solvent, so W there is for solvent, so we have 200.5, and then finally the molar mass of the solute. Remember, our solute is no longer SO2 but H2SO3, and if you calculate its molar mass, you get it as 82. So needing a little help from our calculators now, we have 20.5 by 1000 divide 200.5, and then 82. Yeah, that gives us 1.25. So we have 1.25 molar, which we can write as 1.25 with a small n as the answer to this second question. So the second question was actually a question on chemical dissolution, such that you dissolve a substance in water and instead of just dissolving, it actually reacts with the water. That's what we have here. So this is molality. We've solved molality, at least we've solved 2 examples on it. So we can quickly follow that up with